With that, hello and welcome to this BioProcess International Ask the Expert webcast. I'm your host, Leah Rosen, the online editor for BioProcess International. Before we get started, just a couple of notes. The webcast is being recorded and will be made available for replay in the multimedia section of our website. We've muted the audio lines, but we welcome you to type in your questions for our speaker in the chat window on your screen. After the presentation, we will begin the question and answer portion, and I will ask our speaker your questions in the chat window. Your questions in the window will only be visible to myself and our speaker. So thank you for joining us today. It is now my pleasure to introduce our speaker, Xuemei from Bio-Rad Laboratories.
Thank you, Leah, for the nice introduction, and welcome everyone. Today we are going to talk about the mixed-mode chromatography resins for biomolecule purification. First, we will go over the structural basis of mixed-mode chromatography and how the protein charge state and the ligand charge state are impacted by buffer pH and composition, and how we can manipulate their interactions. And then I will show you some examples to showcase the unique selectivity of mixed-mode chromatography resins, such as hydrophobic cation exchanger, hydrophobic anion exchanger, and hydroxyapatite, which is a calcium affinity cation exchanger. And I will also briefly touch the method development for mixed-mode chromatography. This is a figure that you see often in the textbooks teaching protein chromatography. It gives you the guideline for the selection of an ion exchanger and the matching buffer to purify a protein that you have already known is PI. Typically, we are preparing the feed in a low conductivity buffer to facilitate the binding of the target protein by the resin. Once we finish washing the impurities, we can use an elution buffer that contains high salt concentration to elute the target protein. The same idea can be applied to the hydrophobic anion exchangers. However, the situation gets a little bit more complicated, because if we increase the conductivity of the elution buffer to minimize the electrostatic interaction between the ligand and the target protein, we might actually enhancing the hydrophobic interaction between them. And we also know that protein molecules have their mixed mode nature as well. So the good thing is a protein may use alternative modes to interact with chromatography media in response to buffer conductivity change. This will give us a larger window for buffer manipulation to achieve the binding and elution selectivity. So here is the first example I'm showing you. It's a nucleus C prime, a hydrophobic cation exchanger. So the ligand of this resin has a hydrophobic moiety, that's the benzene ring. It also has a carboxylate functional group. The pH of a buffer can change the charge state of the ligand. If we perform the purification at a pH lower than the pKa of the ligand, such as around 4.8, we're actually dealing with a neutral ligand, and the resin behaves like a traditional hydrophobic interaction chromatography resin. If we move to a more basic site, such as pH 7, the carboxylate group of the ligand will be fully ionized and carry negative charge. So now the resin will work more like a classical cation exchanger. Typically, this resin has a good tolerance of low conductivity, and it provides good clearance of nucleic acids because a hydrophobic resin doesn't bind nucleic acids, and also the negatively charged form have a repulsion to the nucleic acids. I would like to use the next example to show you the unique selectivity of nucleus C prime. So we are comparing new VSC prime with a classical cation exchanger using a pair of basic proteins. The first one is ribonuclease A, which has a pi of 8.7, and cytochrome C with a pi of 10.7. When we load the mixture of these two proteins on a traditional cation exchanger and use a gradient between two buffers, buffer A, 20 millimolar sodium acetate with 150 millimolar sodium chloride at pH 5.5, and buffer B, 20 millimolar sodium phosphate plus 1 molar sodium chloride at pH 7. In a 30 CV gradient, we did not see the separation of these two proteins. However, using the characteristic absorption of cytochrome C at 450 millimeter, we can tell actually cytochrome C is retained by the CX stronger, which is not a surprise because it's more basic. What if we apply this pair of proteins on new VSC prime? Using the same gradient of buffer A and B, now we see two peaks. Again, looking at the 450 absorption, we know that cytochrome C actually is a little earlier from new VSC prime, and the ribonuclease A elution is delayed due to a stronger hydrophobic interaction with the resin. So these two proteins are resolved on new VSC prime. How about a hydrophobic anion exchanger? The example is Nuvia A prime for A. Similar to Nuvia C prime, we have a hydrophobic structural moiety built in the ligand. That's a phenyl group. And then we also have a positive charge on the ligand. Under neutral pH, we expect the high pi proteins are not going to be bound by the resin because of the electrostatic repulsion. On the other hand, the acidic species, such as low pi proteins, nucleic acids, endotoxins, and some viruses, will be bound by the Nuvia A'4A resin. A purification of target protein can be performed in either the flow-through mode or bind and elute mode. We can manipulate a buffer's pH and conductivity to achieve our desired selectivity and recovery of the target protein molecules. Now, let's take a look at the flow-through separation of a map with a PI of 9.1. This is a polished purification step. We want to use DOE to evaluate the important parameters for the clearance of impurities. So as you can see here, the most important thing in this purification is the buffer pH. It affects the clearance efficiency of whole cell proteins, double-stranded DNA, endotoxins, and the aggregate of the target protein, as well as the log reduction of the minute virus of mouse. Another important parameter for this process is the low level. As you can see here, if we continue adding feed to the column, we start seeing the leaching of whole cell proteins. The salt tolerance of this step is visualized here. As we can see, from 0 to 150 millimolar of sodium chloride, we do not see any significant impact on the impurity clearance. That's good. And we also don't see sensitivity of the residence time, which means we can run the purification fast without compromising the product quality. For this particular polished purification, we actually want to achieve the best reduction of MEM. According to the DOE prediction, the MEM is retained by the column during the flow-through separation if it's run at pH 8 with 150 millimolar of sodium chloride in the buffer. On the other hand, The recovery of the target map monomer is the best if the operation is run at pH 6. How are we going to balance it? As we want to use this step to guarantee the overall viral reduction, we actually decided to run the scale-up purification at pH 8 with 10 millimolar of sodium phosphate and 150 millimolar sodium chloride, which would give us a log reduction of MVM over 4.2. And at the same time, we can still get the target monomer recovery over 90%. So here is a case study with the data offered by one of our clients. They used to purify a map using a 3-step process: protein A followed by an ion exchanger and then a HIC column. With Nuvia A'4A, they were able to cut this short into a 2-step process with protein A followed by Nuvia A'4A. At the end, they were able to achieve highly pure drug molecules with over 99% of monomer, and this process also offered an excellent reduction of MVM over 5 logs. Since the process is shorter, they were able to cut down the cost of the production with a higher yield of the final drug molecules. Now, I want to switch gear to talk about another type of mixed mode chromatography media. It's hydroxyapatite. It's an inorganic chromatography material. The composition is shown here: calcium, phosphate, and hydroxyls. So the crystal structure of hydroxyapatite contains phosphoryl groups which would carry negative charges. They interact with the amine groups on the protein surface via charge interaction, just like the classical cation exchanger. The bound protein can be eluted by elevated concentration of sodium chloride during chromatography. The calcium ions in hydroxyapatite can form chelation complex with the carboxyl groups on protein surface. This type of interaction is much stronger than the charge interaction, and we often have to use buffer containing higher concentration of sodium phosphate in order to elute the bound target protein. CHT is known for a good media for the clearance of nucleic acids from the cell culture. It's because of the strong interaction between the calcium ions and the phosphoryl groups on nucleic acids. Hydroxyapatite has been used for protein purification for decades, and Bio-Rad is the first one to introduce the ceramic form of hydroxyapatite for process purification because of the stronger mechanical strength, and the spherical particles can be easily packed into large columns used in downstream production. One of the major applications of CHT is the monoclonal antibody drug production. It's often used as the final polish step, and there are many protocols published. Typically, a map can be bound if we use a buffer containing low concentration of phosphate at around neutral pH. And under this condition, the non-charged endotoxin, the acidic whole cell proteins, will not be bound, and they appear in the flow-through fractions. The bound monoclonal antibody can be eluted either by a sodium chloride gradient or a sodium phosphate gradient or their combination, and we are going to leave the impurities such as the stronger binding map aggregates, the protein A map complex, the charged endotoxins, the more basic whole cell proteins, nucleic acids, and viruses on the column until we strip the column during the cleaning with 0.4 molar sodium phosphate. In the table here, lists the full panel of process and product-related impurities and how efficient the purification of CHT chromatography. Basically, all this impurity can be taken care in a single step. And to show you, I'm going to show you as an extreme case that we have a feedstock of an acidic map that contains over 30% of high molecular weight impurities. So when we condition the feedstock to neutral pH and load it on CHT-XT, we start a gradient between 0 to 1 molar sodium chloride. And we see here in the chromatogram, the monomer, the dimer, and the aggregates are well resolved on CHT. By collecting the fractions between 400 and 600 millimolar sodium chloride elution, we were able to obtain the final eluate that contains only around 3.1% of high molecular weight product-related aggregates. To summarize my presentation, I hope I have shown you examples how the selectivity of a mixed-mode resin can be achieved by manipulating the charge interaction, the hydrophobic interaction, and the metal affinity interaction of the spectral moieties on this chromatography media. And we can obtain the targeted selectivity and recovery by buffered pH and conductivity variation. The salt tolerance of the mixed-mode chromatography media can help us reduce the process step and minimize the feed manipulation. This will help improve the overall process economy. The mixed-mode chromatography method development is pretty intuitive because after we understand the interaction mechanism, we can still use design of experiments and buffer gradient to come up with a chromatography method, just like what you have been doing with the traditional chromatography method. If you are interested in trying this mixed mode resins, you can contact our process specialist at process@biorad.com. Besides sending you the resin samples, we can offer you assistance in method development, process development, and documentation for regulatory support. With that, I want to conclude my talk, and I'm ready to answer any questions you might have. Thank you.
The first question we have is, besides changing buffer pH and NaCl, what else can I try for improving target selectivity and recovery?
Well, this is a good question because we know that usually protein purification is probably a little bit more complicated than just pH and sodium chloride concentration. You can consider using buffer additives such as arginine, glycine, or propylene glycol. Arginine, for example, helps minimize the non-specific interactions and often result in better target recovery and with selectivity. Glycine, on the other hand, has been shown to have modest enhancement effect on hydrophobic interaction, which will allow you to capture the target molecules on the column without using high concentrations of salt. This is very useful if you have a target protein that's not stable in a high conductivity buffer.
Okay, and do you have examples of virus purification with the mixed mode resins?
Yes, our CHT has been used for the purification of viral particles or VLPs by the vaccine industry for a long time. And the Nucleus C' was used to capture a recombinant adenovirus to be used in gene therapy. And most recently, we also work with other clients who are trying to purify smaller viruses such as MDM and adeno-associated virus, AAVs.
Okay, Is Nuvia A prime being used in clinical processes?
Yes, it's being used to produce a drug substance for clinical trials. And in one example, it is used to in a two-step polish purification process to improve the bicarbonate.
And how does Nuvia A prime compare to other available hydrophobic anion exchange resins?
Oh, we have performed some modeling calculation to compare these resins, such as the capital here from GE Healthcare. And our results show that Nuvia A prime 4A is less hydrophobic than those two capital resins, here resins. And this may be translated into a better target recovery in some cases. However, as I have shown in the presentation, a process manufacturing is about the purity and the yield of a target. So we will have to do our due diligence in resin selection and method development instead of simply picking a resin on the basis of a single output like recovery. So if you want to discuss this into a little bit more detail, you can reach us using the email I just shown you.
Okay, great. And it looks like we're running out of time for questions to the audience. If you have any more questions, just go ahead and type them in, and we'll be able to pass them to Xuemei directly, and she can follow up with you. So the last question for now is, I'm interested in learning about design of experiments. Does Bio-Rad provide technical training on design of experiments for mixed mode resins?
Oh, yes. We can set up a Zoom meeting or a webinar to go over the DOA design with you. For example, we can help you select the parameter and their ranges according to your purification needs, so as to understand the interaction between a target molecule and the resin. And we also have a few application scientists who can work with you on your site. If you have performed DOE runs and would like us to go over the results with you to receive help in data interpretation, feel free to reach us too.
Okay, great. Thank you, Xuemei, and thank you to our audience.
You're welcome.
The recorded version of this webcast will be available for on-demand viewing on our website, and as a registered attendee, you'll receive a follow-up email providing you with a direct link. We look forward to having you join us at future BioProcess International Ask the Expert webcasts. Look for those announcements in your inbox. Goodbye.
Bye.